Torques allow objects to accelerate angularly. It is force, but force in a circular motion. To maximize torque, force and distance should be applied perpendicular to each other. The general formula for torque is tau, the Greek letter tau, which looks like a cursive T, equals to force times r, the distance or the radius from the pivot point, sine theta. You want to make sure that force is always perpendicular to the distance from the pivot point. So sometimes this sign can also be cosine theta. The units are Newton meters because force is in newtons, distance is in meters, but this is not a joule. So the SI units for torque is Newton meter. To change torque, we need to change force, we need to change distance, and we could change angle. To maximize torque, you want to have the greatest force, the greatest distance, and an angle of 90 degrees. Forces that were in static equilibrium were at rest or traveling at constant velocity. Torques can also have static equilibrium when it's at rest or traveling at a constant angular velocity. To solve static equilibrium problems, we write a sum of torque net, which is equal to 0, and a sum of F net, which is also equal to 0. Since force is a vector, if we have vectors in the y direction, we have to write a sum of Fy. If we have vectors in the x direction, we write a sum of Fx is equal to 0. If we have both directions, then we have to write two equations. When we solve torque problems, the first thing we do is we locate a pivot point. Sometimes the pivot point will be given, that is the axis of rotation. Other times you need to select the pivot point. If the pivot point is not given, you want to select the point in which there is the most unknowns. So in this example, the pivot point's given to you right here. So we're going to write a sum of torque equation, which is torque of 1 from this force plus a torque of 2, which is equal to 0, because this is in static equilibrium. The general formula for torque was force perpendicular to the distance, which we'll label r. So this will be force of 1 times the distance of 1 plus force of 2 times the distance of r2. This has to equal to 0. So what is R1? R1 is measured from the axis of rotation, which is the pivot point. So this is R1 right here. For F2, the R2 is also measured from the pivot point, and this is R2. So we plug in numbers. But if you notice, if both of these numbers are positive, it cannot equal to 0. So we must account for direction. By convention, the direction of torque is given as counterclockwise as positive, clockwise as negative. So if I look at the problem above, Here is my pivot point. My F1 is located to the left of it. If I push this lever down in the direction of the force, this object is going to rotate counterclockwise. Therefore, this torque is positive. So the F1. If I look at F2, my pivot point is here, and my F2 is given on the right of the pivot point. So if I push on F2, it will rotate clockwise. Therefore, this one will be negative. So, in general, torque is force times the distance from the pivot point. R, F, and R has to be perpendicular to each other. So if I look at my picture here, this is my radius, this is perpendicular, 90 degrees. This is my distance or radius perpendicular to my force. If it's not perpendicular, you want to use sine or cosine to make it perpendicular. I account for directions in the problem before I solve. So locate your pivot point and figure out which way the object will be rotating based on the force that is given. Counterclockwise is always positive, clockwise is negative. This is number 30 from your worksheet. This is a static equilibrium problem. First thing when you get a problem, you want to draw all the forces on the object. We already know that the ladder has a weight of 150 newtons. Since the ladder is uniform, the weight's going to be in the middle. Since it's standing against the wall is pushing against it. So we're going to have a normal force from the wall. Since the wall is frictionless, given it in your worksheet, there will be no frictional force. Remember, normal is always perpendicular to the surface. It will also have a normal from the ground, labeled N2. We do not know if N1 and N2 are the same. It also has a frictional force. The frictional force is going to go towards the wall to prevent the ladder from slipping down. So this problem has 4 forces. And of the 4 forces, we only know 1. So we need to find the other 3. To do that, the first thing I'm going to do is pick a pivot point. Pivot point is the axis of rotation. It is also the point that has the most unknowns. So my pivot point is going to be right here at the bottom. Now I'm going to write a sum of torque equation. So sum of torque is going to be the torque of N1 plus the torque of the weight plus the torque of the bottom. This has to equal to 0. The torque at the bottom will cancel out. Why? Remember, torque is equal to force times perpendicular R. R is the distance from the pivot point. Since the bottom is the pivot point, R is equal to 0. So anything times 0 is 0. So we have 2 torques. This is equal to N1 R1 plus FG RG. This has to equal to 0. Since the angle is not given, we need to solve for the angle because the force and the distance must be perpendicular to each other. So we know the length of the ladder is 4 meters. And we also know that it is 1.6 meters to the wall. So I could find this theta, because this becomes a right triangle, using cosine theta, which is adjacent over hypotenuse. So this becomes 1.6 meters divided by 4 meters, or theta becomes 66 degrees. So the angle here, right here, is 66 degrees. So now I'm going to plug in to solve for N1. So I know my weight of the ladder is 150 because it was given in the problem. My radius, my distance from the pivot point, is going to be halfway up the ladder. So it's going to be 4 meters, because the entire length of the ladder is 4 meters divided by 2. Since my weight is not perpendicular to my lever arm, I need to resolve it. So I'm going to redraw my picture. So if I redraw my picture, that's my ladder. Down here is my pivot point. We know my weight is halfway. When the force vector is perpendicular to the ground, the easiest way to make the force vector and the lever arm perpendicular is to extend the force vector down all the way to the ground. When you do that, this becomes a right triangle. So this is still my weight, Fg. Now it is perpendicular to the lever arm. So when I make the force perpendicular to the earth, I am resolving the lever arm component to make it perpendicular to Fg. We know this angle right here is 66 degrees. We know the hypotenuse is 2 meters because the weight is halfway. So this side right here becomes cosine theta because it is next to 66. So this is cosine 66 degrees. Or you could use the other angle, which will be sine 24 degrees. So now it becomes 150 times 2 cosine 66 degrees. We're going to repeat the procedure for N1. N1, we know we're looking for, so I'm just going to write N1. The R is the entire length of the ladder because my pivot point starts here and my N1 is at the tip. So we know this is 4 meters. Again, this vector is at an angle, so I need to redraw my structure. So if I redraw my structure, this is my ladder. This again is 66 degrees. My N is going to the right. This is my N1 that I drew up there. So we know in math, if we have parallel lines and we have an angle here that is 66, the transverse angle is also 66. If the angle down here is 66 degrees, because this is parallel to this, interior alternating angles are the same. So this also has to be 66 degrees. If the force vector is drawn parallel to the ground, the easiest way to resolve it is make this vector perpendicular to the lever arm. When you make the vector perpendicular to the lever arm, you are actually going to resolve the N component or the force component, because now this up here we know is N1 is the hypotenuse. Right here is perpendicular to the lever arm. So if I use 66, since it is opposite, this will be sine 66, or I could use cosine 24 if I use this angle right here. So N1 times 4 meters sine 66 degrees. So now I'm going to account for direction. My pivot point is on the left of my force. So my weight force is going to push this lever arm down. So it's going to rotate clockwise. So my weight is going to be negative. My N normal, again, my pivot point's down here. This is my ladder or lever arm. It's going to, my force is going towards the left. So when I rotate it, it's going to go counterclockwise. So this is going to be positive. So N1 equals to 33.4 newtons. Now I could write a sum of Fy and a sum of Fx. In my sum of Fy, we have two vectors. We have N2 going up. This is opposed by Fg, which is the weight. This is equal to 0 because this is in static equilibrium. So N2 is going to equal to Fg, and Fg was given as 150 newtons. In my x direction, we have friction going to the right, so I'm going to make that positive, minus N1. This is also going to equal to 0 because this is in static equilibrium. So friction is equal to N1, which is equal to 33.4 newtons. So now at the ladder, which is at an angle here, we have a vector that is going to the right, which is my friction. We have a vector that's going up, that is my N2, or the normal from the ground. So my resultant vector is going to be the Pythagorean theorem of that. So my resultant is going to be N2 squared plus F squared, take the square root. So N2 was 150 newtons squared, plus my friction, which is 33.4 newtons squared. Take the square root. This equals to 154 newtons. So that is the net force on the ladder at the bottom to prevent it from sliding. So we could find my angle here using tangent theta. So tangent theta is opposite over adjacent. Opposite is going to be N2. Adjacent is friction. So this is going to be 150 newtons divided by 33.4 newtons. So theta is equal to 13 degrees northeast. So when you do a static equilibrium problem, first thing you want to do is draw your forces. After you draw your forces, you want to pick a pivot point. Pivot point is the one with the most unknown. Then write a sum of torque equation that has to equal to 0. The pivot point torque will equal to 0. Make sure your force and R are perpendicular. If not, you need to make them perpendicular. If you have a vector, a force vector that's going vertical, perpendicular to the ground, bring the perpendicular to the ground all the way down to make a right triangle, and you're going to resolve the lever arm. If you have a force that is going horizontal, what you want to do is, if this is my lever arm, you want to make the force vector perpendicular to the lever arm, and you're going to resolve the force because this now is perpendicular to the force, the lever arm. After you do that, solve for your unknown. Vectors present in the y direction, and solve for the unknown. And then you want to write a sum of fx equation if there are vectors in the x direction. Afterwards, you want to do Pythagorean theorem to solve the resultant vector and use tangent theta to solve for your angle. This is problem 31 in your packet. See if you could do it on your own and then check your answers. First, you start by drawing your forces. If you drew your forces correctly, you should have 5 total. You should have 1 from the weight here. You should have 1 from the weight of the bar. You should have had a tension force from the rope. The H was given to you, a horizontal force. And you should have a vertical force from at the pivot point because the bar is at an angle. So first you want to do after you draw your forces is pick your pivot point. Your pivot point again should be the point with the most unknowns, and it should be here at the bottom because you have 2 unknowns at that location. So write a sum of torque equation. We're going to have the torque of the weight on top, which is 100 newtons, plus the torque of the weight of the bar, plus the torque of the tension from the rope, plus the torque at the pivot point or the bottom. This has to equal to 0. Since the pivot point is where we measure everything from, this becomes 0. Remember, torque is equal to force perpendicular to the distance from the pivot point. So if I look at the first one, we have 100 newtons. So that's going to be force of 100 newtons times R of 100 newtons plus the weight times the R of the weight plus the tension, the distance of the tension equals to 0. After writing the torque equation, we're going to start substituting in. I'm going to start with the vertical vectors. So I'm going to start with the 100 newtons. So the force 100 newtons is 100 newtons. My distance is going to be 6 meters because this is my pivot point and it's at the edge of the length of the bar. So that's going to be 5 meters plus 1 meter. So that's going to be 6 meters. I'm going to redraw my picture. This is my vector, 100. If you notice, it is not perpendicular to the lever arm. It is at some angle. Since it's perpendicular to the earth, I'm going to bring it all the way down to make a right triangle with the ground. So when I do this, this is still my force of 100 newtons. This right here is a component of the lever arm. Because why? My hypotenuse is 6 meters. We know this angle is 40 degrees because it was given in your worksheet. Since I am solving for this side, because this side is perpendicular to the force here, this will be cosine next to 40 degrees. So this is 100 newtons times 60 cosine 40 degrees. Next, I'm going to plug in for the weight of the bar. The weight of the bar was given as 200 newtons. My distance of the bar is going to be 3 meters because it's going to be 6 meters is the total length, and it's midway, so it's going to be half of that, which is 3 meters. So if I redraw my picture here, this is my pivot point again. This is my bar. If you notice, my force of the weight is midpoint here. Again, it is perpendicular to the earth. So I'm going to bring that vector all the way down. So it's perpendicular to the ground. And this is still my FG. If you notice, again, we are going to be resolving the lever arm because the lever arm here is now perpendicular to my force. The distance of my hypotenuse is going to be 3 meters. This angle is still 40 degrees. Since I'm using 40, this will be cosine 40. Or if you want to use this other angle up here, it will be sine 50. So this will also be cosine 40. Plus my t, which I do not know. And then my r is going to be at 5 meters. Because if you notice, it is 1 meter in from the bar, edge of the bar. So it's 5 meters total. So I need to redraw the tension vector because it's not perpendicular. So that's my T. This angle was given as 20 degrees. We know this angle down here where the pivot point is 40 degrees. That was also given. So if I look at this picture, the line, the dashed line, and the earth are parallel to each other. So this angle here is going to be 40 degrees. So this total angle is going to be 40 plus 60, or I'm sorry, 40 plus 20, which is 60. So to make the right triangle, what I'm going to do is I'm going to take my T right here, my tension, and I'm going to make it perpendicular to the lever arm. So when I make it perpendicular to the lever arm, this is the side I'm going to look for. So if you notice, it is opposite the 60 degrees. So that's going to be sine 60 or cosine 30. So I'm going to use sine 60. Solve for T. Now I'm going to do direction. So if I look at my direction, in the first picture, this is my pivot point here. My force is pulling it, this levered arm down, so this is going to rotate clockwise. So my force here is going to be minus. My pivot point is here again. For the second, the weight is pulling my lever arm down, so it's going to go clockwise. So this is negative. For the third vector, my tension, my pivot point is still located in the same direction. My tension is pulling it in the opposite direction, so it's going to go counterclockwise. So this one is going to be positive. So solve for T. You should get 212.3 newtons. Now I need to write a sum of Fy. My sum of Fy, I'm going to have 4 vectors. I'm going to have my pivot point in the vertical direction going up. I'm going to have a tension Y component going up. because my tension is at an angle, so we have to make them into X and Y. My weight FG is going down. My weight F1 is going down to 100. This is equal to 0 because we're in static equilibrium. So V is equal to Fg plus F100 minus T sine 20. So if I plug this in, this is going to be 200 newtons plus 100 newtons minus 212.3 newtons sine 20 equals to 227.39 newtons. My sum of Fx, we only have two vectors. We have the h on the bottom given minus my tx. This has to equal to 0. So h is equal to tx, which is t cosine theta, which is 212.3 newtons cosine 20 equals 199.5 newtons. Now my pivot point has a h going to the right. It has a v going up. So if I draw my parallelogram by shifting my vectors with the same magnitude and direction, my resultant starts from the tail to the tips. This is my r using Pythagoras. Now I'm going to solve for r using Pythagorean theorem. So v squared plus h squared, take the square root. V is equal to 227.39 newtons squared plus 199.5 newtons squared. Take the square root. This is equal to 302.5 newtons. Tangent theta is what we're going to do to find the angle. So I'm going to measure from the horizontal going to the north. So it's going to be opposite over adjacent, which is V over H. This is equal to 227.39 newtons divided by 199.5 newtons. So theta becomes approximately 48 degrees northeast.